Welcome to a new mini-series. In this series, we're going to be covering simulation-based estimation methods. Up to this point in the course, we've focused on maximum likelihood estimation, and this is a powerful tool if you have a model that can be specified in a way that will admit a likelihood function. However, there might be some models where you can't write down the likelihood, or the likelihood is too intractable to estimate by straight maximum likelihood estimation. We covered an example of this with the mixed logit, where we had a very complicated integral that was in our likelihood function. However, there may be other situations where you don't want to commit to a particular distributional assumption, or there could be other specifications in the model that make it too complicated for simple maximum likelihood to handle. This is where Generalized Method of Moments, or GMM, comes in. GMM is incredibly flexible and allows us to estimate a complicated model without committing to any distributional assumptions if we don't want to. GMM can also be generalized to other forms of estimation like simulated method of moments and indirect inference, which we'll talk about in further videos in this series. But for today, we'll just focus on the basics of GMM and build up to those more complicated generalizations in later videos. If you're watching this video, you might have already taken a graduate level econometrics class, and in that class, you undoubtedly were introduced to GMM. GMM is really popular because it nests a lot of common estimators that we see in introductory econometrics courses. This includes OLS, instrumental variables and two-stage least squares, and nonlinear least squares. We can also asymptotically replicate maximum likelihood estimation using GMM if we specify the right moment conditions. And unlike maximum likelihood, we don't need to assume an exact distribution of errors to estimate a model using GMM. Now, if we want to simulate that model, we're going to have to commit to a distributional assumption, but not necessarily for estimation. So let's walk through how to do this in a linear regression model. You might have already seen this in a prior course, but just wanted to cover it for completeness sake. So let's consider a basic regression model with two covariates and an intercept. We're going to make the fundamental assumption that the expected value of our error term is conditionally independent of the x's. From this assumption, we can build a system of equations with three equations and three unknowns. If we were doing maximum likelihood, we would make an additional assumption in addition to the conditional independence assumption that the epsilon has a particular distribution, typically normal. So once we have this conditional independence assumption, we can write down population moment conditions, and then we can substitute in y minus x beta for epsilon in those population moment conditions. And then here we have a system of three equations with three unknowns. The three unknowns are the betas, and then we have the three equations implied by the moment conditions. And then if we want to actually estimate this, we take the sample analogs of the expectation operator, which is just going to be 1 over n times the summation over the sample size. And we're going to call this system of equations g of beta. And in this case, we have what's known as exactly identified GMM. And we can show that the estimates of the betas are given by the minimization of this j function, where j is basically the squared difference of these g functions multiplied by n for convenience. And if we work through the math, we can show that for OLS, this exactly identified GMM will give us the same exact solution as the least squares estimator. So hopefully that is a helpful review to get some fundamentals. Let's also think about what happens if we have more moment conditions than parameters. So in this case, we would need to specify a weighting matrix that would allow us to say how much weight should be given to each of the moment conditions. So in that case, j is going to be a function of both the parameters that we're trying to minimize the objective over, and this weighting matrix, which we call W hat. And we just stick this W hat weighting matrix in the middle of the two G function dot product, and then we'll get the over-identified GMM estimator objective function. As you might have seen in a prior course, there's extensive econometric theory about what the optimal weighting matrix is. In this case, we're going to want to weight each moment by the inverse of the variance, there's also good asymptotic properties of this GMM estimator, especially when using the optimal weighting matrix. Let's think about another way that we could estimate OLS using this moment condition mentality. In the example I showed you a moment ago, we had k equations where k is each of the x's, and then an additional one for the overall mean of epsilon. We just had 3 equations, 3 unknowns. We solved it, and we got the analytical solution that looked like OLS. Now, we could alternatively use the OLS residuals as moments, and in this case, we want to minimize the residuals. So in this case, we're trying to match y with x beta hat as closely as possible. So in this case, we could set our g function to be y minus x beta. This would give us n moment conditions, and I put moment conditions in quotation marks because they're really residuals. And then we have the same k plus 1 parameters that we want to estimate, just like we did earlier. So here we can use the n by n identity matrix as our weighting matrix because we have more moment conditions than parameters. So without any prior information, we don't know which of the residuals we should put more weight on. So let's just put the same amount of weight on each of them. And what we'll get here is just exactly the OLS objective function, and we'll give exactly the OLS estimator for the formula for the estimator. So why do we want to do it this way? Well, usually it has better numerical properties. It's not going to be as finicky as trying to do the exactly identified GMM that I showed you originally. So let's take this same approach and apply it to the binary logit model. We have our G function, which is these same moment conditions. In this case, our residual is going to be y minus p, or p hat, instead of y minus x beta hat. And we're applying the logit probability function. So this is intuitive because y takes on values 0 or 1, and p takes on any value in the unit interval. So these are our moment conditions, and then we're going to have the same J formula that we had before, which is n times the dot product of g of beta with itself. And then we can also apply the alternative approach where we just want to use y minus p as our moment conditions, quote unquote, and we're going to get the same sort of setup with n moment conditions and k plus 1 parameters to be estimated. We're over-identified. Let's use the identity matrix for the weighting matrix. And this approach to GMM is also going to give us something called the nonlinear least squares estimator. So that's a little bit about GMM and how it links with OLS and nonlinear least squares. And in the next set of videos, we'll talk about how we can generalize GMM to situations where we can't necessarily write down the moment conditions in a particular way that's useful to compute those moment conditions. We might need simulation. And so in the next video, we'll introduce 3 simulation-based approaches: maximum simulated likelihood, method of simulated moments, or SMM, and method of simulated scores. We'll talk about the pros and cons of each method and how they relate to maximum likelihood estimation, or GMM, as we've covered already. So I hope to see you in the next one.